Okay, so in the end of section 2, we talked a little bit about the parametric representation, and I referred to that as a vector. So 1.3, we're going to talk in more detail about vectors. Okay, so simply a vector is a matrix with one column. Okay, so a matrix with one column is called a vector, okay, or sometimes called a column vector, ultimately referring to the same thing. Okay, so matrix with one column is a column vector. Okay, at its core, a vector is an ordered list of numbers. Okay, now we know several other ordered lists, and vectors are going to tie directly into this, right? So we've talked about an ordered pair. We had a system in section 1 that the solution was 2, 3. Well, we could write that as a vector. Okay, 2, 3, the vector. And ultimately, that still corresponds to the same thing. Okay, so to give you an example, right? Say we have a vector u, okay, and you will usually see vectors denoted with bold letters. Now, in my handwritten notes, I can't always represent the bold terribly well, but if you look in the book, you look on your homework assignments, bold letters correspond to vectors. So a vector u, let's say it's 2, -1, it's a nice vector. Let's make another vector v. Maybe it's not as pretty. We'll say it's 1/6, 1/7. Okay, so those are a couple of specific vectors. Maybe we have a really generic vector here, w. That vector w, then we'll call it x1, x2. Okay, so being real generic with our notation. Or maybe if we wanted to, since we called it w, ultimately this is just a naming, right? Maybe I want to give the coordinates w1 and w2. Okay, and so those w's then would be not bold-faced because those are the coordinate part of it. Okay, so vectors are relatively easy things to work with most of the time. We do a lot of operations with vectors. So let's take our vector u and our vector v, and let's add them. Okay, well, we have our vector u, 2, -1, plus, not equals, plus our vector v, that's 1/6, 1/7. And if I add them, you just add the components. So 2 in terms of sixths would be 12/6. So when you add, you're going to get 13/6. And then -1 would be -7/7. So if I add 1/7, I'm going to get -6/7. And so that would be the sum of those two vectors. Okay, so adding vectors is a pretty easy task. We also can multiply vectors by scalars. So let's say 3 times u. I'm going to take 3 and multiply it by my vector u, 2, -1. And let me bold that u a little bit, indicate that's a vector. And so then we multiply the coordinates accordingly. So 6, -3. And there's my vector 3u. Okay, so I can do that operation as well. And then we could always tack these things together. So let's say 3u minus 6v. Okay, well, first let's find 6v. So that's 6 times 1/6 and 1/7 is the coordinates. So when I multiply 1/6 times 6, I get 1. And when I multiply 6 times 1/7, I get 6/7. So if I do 3u minus 6v, I'm going to take 3u, which was 6, -3, and I'm going to subtract 1 and 6/7. So 6 minus 1 would be 5, and -3 times -3 minus 6/7. So remember, -3 in terms of sevenths would be 21/7. So if I take away 6 more, then I'm going to be at 27/7, but negative. Okay, and so that would be adding and subtracting vectors. Okay, so we have several properties for vectors. Okay, first property is one you're familiar with. That's commutativity. U plus v is going to be the same thing as v plus u. Second property is another one you should be familiar with. It's called associativity. That is, I can arrange these parentheses in any pairwise method. So u plus v and then add w, or I could do u and then add v plus w. So whether you add the v and w first or whether you add the u first, gets you the same thing. Okay. We also have a very important zero vector. Okay. So note these are all vectors right now. I'm not necessarily bolding them in my drawings here, but a zero vector, okay, that's the same thing, of course, by commutativity as u0 plus u. And a zero vector, if you think about adding 0 to a number, you should just get u. Okay, a fourth property, we have negative vectors. We have an additive inverse. So u minus u is, of course, the same thing as minus u plus u, and that should add up to the zero vector. Okay, that's what an additive inverse means. And then we have properties for scalar multiplication. So if I take a scalar c and I multiply it by u plus v, okay, that's the same thing as distributing it. So cu plus cv would also work there. Okay, and then 6, I have associativity for the scalars. So if I have cd, which are both scalars, times a vector u, that gets me the same thing as cu plus du. Now where u is the vector there. Right? That's distributivity for scalars, I should say. And then associativity for scalars, it doesn't matter what order I do the scalars in, whether I do d times u first and then multiply by c, or whether I multiply the scalars c and d and then multiply that result by u. Either way works. And then we also have a multiplicative identity. We have a one scalar, 1 times u is equal to u. Okay, so 1 here is a scalar, u is a vector. Okay, and those are our properties for vectors. Okay, so we can easily add, subtract, and then multiply by scalars for vectors. Now, we don't talk about multiplying and dividing just yet. We've not talked about multiplying matrices at this point. That's something we're going to get to very soon. We've not gotten to that yet. So we're not multiplying vectors, we're just adding and subtracting. Okay, and so we said that these are an ordered list. So ultimately, a vector looks a lot like graphing. So if I take my vector 2, 3 that I had earlier and compare that with the ordered pair 2, 3, and take you a little Cartesian coordinate sketch here, right? The point 2, 3 is here. Okay, well, this is the point 2, 3, and so that corresponds to the ordered pair 2, 3, where my vector is the line that connects that point 2, 3 to the origin. Okay, it's that pathway. Okay, so my vector is this pathway where the point, the ordered pair, is just the single point here. Okay, so I have my vector 2, 3. Okay, let's take another vector. Let's make this vector negative 1, 1. Okay, and so let's graph that on here. I've got negative 1, 1. I've got that point there. And then I can graph my little vector coming off of that. Okay. All right, so let's call this vector u, just for convenience. Let's call this vector v. Okay, so I've got my u vector and I've got my v vector on my little graph here. Okay, so let's look at u plus v. Okay, well, u plus v, well, I add the components, right? So I'm going to take 2 and negative 1 and add them and I get 1. And I'm going to take 3 and 1 and add them and I get 4. Okay, so that point u plus v is at 1, 4. Okay, so let's put that point on the graph here. Went the wrong way. 1 and then up 4. Okay, I'm going to draw it with a little dashed line so we can tell it apart from my other two. And so this is u plus v. Now, as I look here, this makes a familiar shape to us. This is a parallelogram. Okay, so the sum of two vectors forms a parallelogram. So the 4 points, the 4 vertices on this parallelogram are u, v, u plus v, and my origin, my 0 vector, okay, at the origin. Okay. Now, ultimately, what we're going to talk about is linear combinations. Okay. So we know what linear equations are. We know what vectors are. Okay. We know we can add, subtract, and multiply by constants. So if you imagine u here, this is one copy of u. Well, I could extend u out to make a second copy. And I could extend v out to make a second copy of it. Okay, and my figure's not going to be super pretty here, but we'll work around it. Okay, and I could make a full grid out of this idea, right? I could keep extending that one up. I could keep extending that one up. This one would extend off of here and off of here, and you can start to see this grid that would form, okay? And so if I look here, this point right here, I can just count on my grid, right? This is one copy of U and two copies of V to get there, right? Two copies of V, one copy of U, and they meet. So this point is U plus 2V. Right? And if I went out another one out here, this would be U plus 3V. If I come out here, I'm going to be at 2U. Right? And all the points along this will be some multiple of U with some appropriate multiple of V. Okay? So if I'm on this line, I have no multiples of V. All right? This is just U, 2U, 3U, and on up. If I'm on this line, I have no multiples of U. So V, 2V, 3V, and on up. Okay? So we can use that graphical information to help us solve some linear systems. Okay? Because imagine now that I have the point or the equation 3U plus 3V. Okay? Well, I can take those values I have for U and V and determine, right? 3U is going to be 6 and 9. 3V is going to be -1 and 1. I'm sorry, -3 and 3. Didn't multiply it. There we go. And then when I add them together, I'm going to get 3 and 12. Okay. So I want to think about this in terms of a linear system, though. So instead of putting 3 here, let's call this a variable x1. Okay. So my vector u is still 2, 3. And then let's call this a variable. Let's say x2. And my vector here is still -1, 1. But I still want this to equal 3, 12. Okay. Now, I know from what we've already done before that these values are 3 and 3. Okay. I know if I put 3 here for x1 and 3 here for x2, that it will satisfy this equation. Okay. But ultimately, this corresponds to a system of equations. Okay. So let's look at that system. Okay. So I have my equations here. And let's write down what these equations would be as a system of equations instead of as vectors. Okay. So this is x1 times 2. So I have 2x1. Sorry, adjust the camera just a smidge. So I have 2 copies of x1. Well, down here I have 3 copies of x1 in the second equation. Okay, I have -1 copy of x2 in the top. On the bottom, I have just 1 copy of x2, so that's going to be plus instead of minus. And this one is equal to 3, and this bottom one is equal to 12. So there I have a linear system. And I can take that linear system and put it in a matrix, an augmented matrix, right? And I can apply my row reduction algorithms to take care of this, okay? Now, we know that this is going to reduce because we know that the solution is 3 and 3. So if you reduce this matrix, you'll find that this is the equivalent matrix, okay? So I'm going to take a moment here and show you that on the calculator, okay? So I have a TI-83 plus, 84 is largely the same. Okay, so as you're looking at this, you have these previous matrices I did. There's a matrix button here. I know it's not super in focus, but we can work around it. A matrix button there right above that X inverse key. Okay, so you're going to go second matrix. Okay, go over here to edit. So move your arrow over to the right. Okay, and then that first asks you for the size of your matrix. So my matrix here is 2, not 23, 2 by 3. So now I have my matrix, and I'm going to type in my numbers: 2, -1, 3, 3, 1, and 12. Okay, then you need to quit. Go back to your main screen. So I'm here on my home screen now. Go back to matrix, and in the middle here is a math menu. And down here toward the bottom of the math menu at B is RREF, which should be familiar to us from the last section. That's reduced row echelon form. So I can take RREF, I can take matrix A, and ask it to reduce it. And you see there's my 1, 0, 3, and 0, 1, 3. Okay. You can also get the same place with the row operations. Okay, so we're going to do plenty more examples of things like that to work with, but that gets you a start. Okay. So what we see here then is that the vector 3, 12, right? Remember what we had? We had that 3 times my vector u plus 3 times my vector v added up to the vector 3, 12. Okay, so 3, 12 is a combination of these two vectors. Right? And so that's exactly the definition we're going to use here. Okay, so we're going to talk about linear combinations. That's what we need vectors for. Okay, linear combinations. So given vectors, and it doesn't just have to be two vectors, it can be any number of vectors. So v1, v2, all the way out to some vn. So given a list of vectors, and these vectors are represented by real numbers. They are in Rn, okay? So my vectors that I had here before, u and v, and then the vector 3, 12 that we just dealt with, these three vectors are in R2, okay? Why R2? Because they have two coordinates. So R2 is your conventional Cartesian coordinate plane that you're so familiar with, the XY axes, okay? That is R2. Those vectors are in R2. So for my definition here, I have vectors that are in Rn. So maybe they're 3-dimensional, maybe they're 4-dimensional, maybe they're 5-dimensional, whatever it might be. And then I also have a list of scalars, so C1 through, my dot, Cn. Just a little out of focus. A little better. Those are real number scalars that are multiplied. Okay, so I've got vectors and scalars, and I'm going to do some operations on them. Okay, then a vector y is called a linear combination of my vectors, so v1, v2, all the way out to vn, with linear weights, which are my scalars, c1, c2, cn. I forgot the s, linear weights. Sometimes we will just refer to them as weights. As you've kind of already seen in the class, we tend to drop off the linear sometimes because we know it's linear algebra. So we shorten linear system to system, or linear combination to combination, or linear weight to just weights. Okay? If we have an equation, y is equal to c1, v1, c2, v2, and that continues all the way out to the last one, cn, vn. Okay, so it's a linear combination if we can set up an equation that makes that the case. Okay, so we would say y is a linear combination of the set of vectors. Okay, then we talk about, the next thing we talk about is span. Okay, span is all linear combinations of a set of vectors. Okay, so you have your set of vectors, you take all the linear combinations, and that gives you the span. Okay, so we denote that, denoted with span, and then we would put our vectors inside here. Okay, so let's look at a couple of things here. Take my vector u that we had before, right? That was 2, 3. Imagine what its picture looks like here. Okay, I've got my vector u. Okay, well, if I just look for the span of u, so that's all the multiples of u. Okay, so I can continue on in this direction, 2u, 3u. I could even go negative, right? I could go negative u. Okay, So the span of U then is a line through the origin. Okay. Well, let's expand our horizons. Let's make it the span of U and V. Okay, so I come back to that picture I drew before, right? The span of U and V is all of these combinations together. It's this line, it's also this line coming out the other side, and it's all the ones in between. And I could remember I could have fractional ones in between here too. So actually the span of all of these is this whole plane. I can pick any spot and I can find its coordinates on that grid. Okay, I can come up with a combination of it. Okay, so the span of U and V is actually equal to all of R2. Now the span of just V, it's also a line through the origin, right? It's just a different line. Okay, so it's all the multiples of those vectors. Okay. Need one more definition here for vectors, are that vectors are only equal if all components are equal. Okay, so vectors are only equal if all components are equal. So we're just making the relatively straightforward point here that the vector 2, 3 that we've been using is not the same as the vector 3, 2. Okay, so an important caveat there. Okay. Okay. We're going to plot a couple of vector ideas here. So I take my vector, new vector u here that we will call 4, -1. Okay. And our task is going to be to plot, not plat, plot u, 2u, -2u, and 3/2 u. Okay, so draw a little coordinate plane here. My coordinate 4, -1, so that gets me that point. So I have u, right, that's u. 2u then will be double that. Okay, think about what 2u is. It would be 8, -2. Okay, so there's 2u. Now -2u is going to be -8 and a +2. Right, so you're multiplying those coordinates of 2. It's going to come out the other way. No, my figure's not going to be drawn to scale here, right? So that's -2u. Now 3/2 u, right, would be halfway between u and 2u, right? So we would get that whole line, okay? Now we can also do this in R3, right? This one's a pretty easy one because it's in R2, right? We like two-dimensional vectors. They're easy for us to deal with. We can also expand our horizons out to 3 dimensions, though. So let's say I have the vector 1, 4, 6. Okay, and my drawings are not works of art here, but should get the idea. Okay, so 1, 4, 6. So I've got 1 on the x-axis, 4 on the y-axis, and then up 6 on the z-axis. So my point here really comes out this way. Okay, so imagine our grid here drawn. See, it makes a box shape there. And then my vector comes out to this corner here from the origin. Okay. So a vector is sort of extending up at you as you look at that image. Okay. Play around on Desmos.com for some three-dimensional images. Wolfram Alpha can also help you with some three-dimensional visualizations if you're imagining that. And so 2 copies of V, right, would extend out a little further, right? It's closer and closer to us. -V, right, would go down inside that page. Okay. So a few different options there. Okay. Now, zero vectors, right? Zero vectors are also great fun. They're easy to deal with, right? So a zero vector is in Rn. A zero vector is a vector that has a whole bunch of zeros. Okay, we like zero vectors. They're easy for us to deal with. Okay. So geometrically then, like I said, if we have got R2, and I've got two vectors, one vector just gives me a line, okay? But let's say my two vectors are 1, 2, we'll call this U1, and then my second vector is U2, which will be 2, 4. Okay, but what do we notice about U2? U2 is actually the same thing as two copies of U1. Okay, so even though I have two vectors here, I don't actually have something that spans or covers all of R2. It only covers one dimension because this is two copies of the first vector. Okay, so if you have two vectors that are not overlapping, you get all of R2. Okay, so if I go to R3 then, if I have one vector, I still have a line, right? So one vector is a line. Two vectors makes a plane. Okay, so that's in R2's case, that's the whole thing. Three vectors in R3 is going to be the whole space. It's going to be all of R3. Or if I just have two vectors that aren't multiples of each other, remember, if they're multiples of each other, that doesn't give you any new information about your space. And then that's going to be a hyperplane. It's going to go above plane. So two vectors is just the plane. Three vectors would be a hyperplane. So if I go up to four vector, R4, but I only have three vectors. And we'll do some more things when we talk about linear independence a little later in the chapter as well. Okay, so chapter 1 here really covers a lot of definitions things, a lot of terminology, and we build these terminologies kind of on top of each other. So you see how one thing builds into the next, okay? Right now we're talking about linear combinations, okay? So we're going to look at a couple of examples involving linear combinations. Okay, so I have a vector A1. That vector is 1, -2, and -3. I have a vector A2, and that vector is 2, 5, 6. And then I have a vector B, and that vector is 5, -1, -9. Okay, and so the question is B a linear combination of A1 and A2? So is B a linear combination of A1 and A2? So let's think about what we're looking for then. We're looking for the weights that this would correspond with. So let's call it X1, A1, X2, A2, right? X1 and X2 then are my weights that I'm looking for, and I want that to equal B. Right? Well, we know what A1 is. It is 1, -2, -3. We know what A2 is. It's 2, 5, 6. And then B is 5, -1, -9. Okay. Well, this is a linear system, right? We just talked about how I could write a linear system that corresponded to this, right? This would be X1, 2x2 equals 5, -2x1, 5x2 equals -1, and -3x1 plus 6x2 equals -9. Okay, so I have more equations than I actually do variables. So sometimes that's called an overdetermined system. Okay, but overdetermined systems can still have solutions. In this case, I would have a matrix, 1, 2, 5, -2, 5, -1, and -3, 6, -9. Okay, and I'm going to reduce that matrix. Okay, I use your favorite, and as I look at my notes here, I want to make sure I get the numbers to come out the same. So this A1 vector should be -5. Sorry about that. That should be -5. Otherwise, we're not going to get this to come out like I want it to. So I want to change those to -5. Sorry about that. And I apologize. I don't want to re-edit the whole video, so I apologize. Okay, so -5 to make that. Okay, so I want to row reduce this. Remember, this is augmented. Okay, it looks like just a coefficient matrix because it's 3 by 3, but it's augmented right now. I already got the equal sign. I got b on the other side. Okay. Now you can do all your favorite row operations on this. Okay. I think it's good practice to go through and do it. Okay. You don't have to. I'm going to just show it to you here. I'm just going to give it to you. But it's good practice to go through and do it. But we get 1, 0, 3, 0, 1, 1, and 0, 0, 0 at the bottom. Remember, this is augmented. So this tells me then that my weights here, x1 is equal to 3, and x2 is equal to 1. Okay? So what that means is if I take 3 copies of 1, -2, -5, and I add 1 copy of 2, 5, 6, well, this is going to be 3 plus 2. That gets me 5. -6 plus 5 is a -1. And -15 plus 6 is a -9, which is exactly the vector I had over there. So is B a linear combination of A1 and A2? Yes, it is. Okay. So we can use the augmented matrix to solve the vector equations. Okay. So vector equations and augmented matrices are equivalent. Okay. The next page here, we're going to write that it's not really a theorem, but it's sort of a theorem-like idea. I will just write that directly here. Vector equations and augmented matrices have the same solution set. Okay, so you can go back and forth between the vector equation and the augmented matrix. Okay. All right, so next I want to look at a little bit from the book. I don't like to always share directly from the book because I know ultimately you can read it, but sometimes they have good drawings that I can work with easily, and so I like to use those to my advantage when it makes sense. Okay, so as we look at our text here, it's on page 30, you can see one of these grid setups. Okay, so figure 8 identifies the linear combinations of these two vectors, -1, 1, and 2, 1. Okay, so you can see the vectors v1 extends out to the left here and makes a grid. 2v1, 3v1 are marked there for you. v2 extends out to the right. 2v2 and 3v2 are marked there. So you can read off any point off this grid. So -2 v1 plus v2 is down here in the lower right. So you can use this grid or a grid-like thing to read that off. Just find where your given starting vectors are and then locate what you're looking for based on that grid. Okay, that grid can be very useful. Okay. All right, now the next thing I wanted to show here, let me skip ahead a couple of pages, is that you sometimes need the row operations. The row operations, it's nice that we have the calculator and we can always use that to our advantage, but sometimes the row operations are necessitated based on the setup of the problem. Okay, so as I take a look at practice problem 2 here, for what values of h will y be in the span of v1, v2, and v3? Okay, so we want to take a look at that problem. So I got v1, v2, and v3 there. Okay. So first, let me write those vectors down. Right, I've got v1 is going to be 1, -1, 2. v2 is going to be 5, -4, -7. And v3 is going to be -3, 1, 0. And then my vector y is going to be -4, 3, and h. Okay, so I can't easily enter that h value like that in my calculator and have it do the row operations for me. Okay, So I want to figure out if y is a linear combination of these three. So ultimately, I am still looking at a matrix, right? It's going to be 1, -1, 2 in the first column, 5, -4, -7 in the second column, -3, 1, 0 in the third column, and then -4, 3h in my augmented column. And I want to solve this matrix, okay? So I've got a pivot in the upper left, just like I like, so we're good to go with that so far. And so I want to get zeros below it. So I'm going to take row 1, I'm going to add it to row 2 and replace row 2. I'm also going to take -2 copies of row 1, add those to row 3, and replace row 3. Okay, so I'm going to do these two row operations at once, okay, because I want to get a 0 here in row 2, and I want to get a 0 here in row 3. Okay, so first row is unchanged. My row below that then, so I'm adding 1 and -1, I get 0. I'm adding 5 and -4, so I get 1. Well, that'd be good for later as we start to identify our pivots. Adding -3 and 1, I get -2. Don't forget to add the last for a column that gets left off by students a bunch of times. -4 and 3 is going to be a -1. Okay, I'll draw my bar there. Remember, it's augmented. Third, then I've got 2 copies, -2 here. So -2 and 2 is going to make 0, just like we want. -2 times 5 is a -10. I'm adding that to -7. I'm going to get a -17. Okay. Then I've got a -2 times a -3 is a +6. I'm adding that to 0, so I get a +6. And then don't mess up the h one here. That can be tricky. -2 times a -4 is a +8. And then I'm adding that to h, so I actually have 8 plus h. Okay, so making progress here. Going down now, I want to get a 0 here, so I've got first pivot, 0's below, we're good. Second pivot now, I want to get a 0 below it. So I need 17 copies of row 2, add that to row 3, and replace row 3. So that was equivalent, so this one will be equivalent as well because it's linked by a row operation. Row 1 is unchanged. Row 2 is actually unchanged, okay, because row 3 is the row being replaced. Row 4 now, 0 plus 0 is 0. 17 times 1 is 17, and 17 minus 17 is 0. 17 times a -2 is a 17 times a -2 is a -34. Add 6 to that. Okay, that's a -28. No, -34 plus 6, -28. -17 plus 8 plus h. Well, -17 plus 8 is going to leave me with -9 plus h. Okay. All right. Now, I want to work up from there, but I can make some observations here even before I try to get this totally in reduced row echelon form. I'm going to go ahead and scale this. So I'm going to take row 3 and divide it by -28. I know that feels like an ugly calculation, but our top 2 rows are unchanged, so it's not too bad. Now living with 1 there, and then this will be -9 plus h over -28. It looks ugly, but it's really not that bad because we can make some observations. We have a triangular matrix, which means I have a triangular system. When I have a triangular system, right, I can make an observation then that says that, well, this is going to be consistent anytime because x3 is equal to this value no matter what. Okay? So y is a linear combination of those vectors for any value of h. Okay, so y is a linear combination for any value of h there. Okay? Now, you may have noticed I've made a writing mistake, a writo, if you will. The first vector here was supposed to have 1, -1, and 2. Okay, so the computations for what I've written down here are absolutely correct. Okay, So this works for any h, okay? So y is a linear combination for any h, okay? Now, we could have a different situation if I go back to the one the book actually had there, where I have a -2 then for v1. Well, if I make this -2, let me just start up a new system here to give us another example. Okay, so I'm going to do the same style of row operations here. I'm going to take row 1, add row 2, and replace row 2. I'm going to take 2 copies of row 1, add row 3, and replace row 3. That's going to give me the same first row, one across. It'll give me the same second row that I got in the last one. So that's 0, 1, -2, and -1. All right, just adding those first 2 rows. 1 and -1 makes 0. 5 minus 4 is 1. -3 plus 1 is -2. And -4 plus 3 is a -1. Third row, then, I've got 2 and -2 is going to be 0. 10 and -7 is going to be 3. 2 times 5 is 10. 2 and -3 makes -6. Add that to 0, I get -6. And so then 2 times 4 there is going to now be -8 plus h. Okay, similar row operation here to get 2. So I get -3 copies of row 2, add that to row 3, and replace row 3. Again, it's a good habit to list that second second row, I should say, that you're adding. That will help keep your computation straight. That should always be the one that's getting replaced. Okay, so row 1's not going to change. Row 2 then, not going to change. Row 3 now, 0 plus 0 is 0. -3 and 3 is 0. -3 going to give me a +6 here. +6 and -6 is going to be 0. Okay, and now -3 is going to give me a +3 there. So 3 minus 8 is going to be a -5 plus h. Okay, now I have a different style of result. Okay, because now this would be my pivot. The only thing that would make that not be a pivot is if it's 0. Okay, if it's a pivot, then this system is inconsistent. Okay, so if pivot, system has no solution, or the empty set symbol. Okay, if it's a pivot, there's no solution. So I need it to not be a pivot. So -5 plus h needs to be 0, which means that h needs to be 5. Okay, so if I change that v1 vector, just that one negative sign difference makes a huge thing. If I have a +2 for that v1 vector, then any h will work to be a linear combination. But if I have a -2 for that first v1 vector in that third position, then h could only be 5 in order to be a linear combination. So y is a linear combination if and only if h is equal to 5. Okay? So once again, take a look at the homework problems there in that section. They should follow a lot of these same themes. Okay, use your textbook examples. Let me know how I can help, and then we will get on to section 4 next, where we will tie it into the matrix equation. We talked about the vector equation now in systems of equations, so we go to 1.4 then is the matrix equation. And I'll see you in that video.